All right, so now we have a completely different problem. So far we've been talking about how do I reduce the number of tags and how do I reduce the tag size. We have one more problem in comparing the given tag from the address to the tag that is stored in the cache. So in this example, I have 4 cache blocks. So if I give you an address, then I need to compare the tag in the given address to all 4 of those tags. And if you go back to lecture 17, we talked about a structure called CAM, Content Addressable Memory, that is capable of performing these parallel comparisons. While we have the capability to do it, there is a limitation to how much we can scale the structure. So when you increase the size of the cache to, let's say, a few kilobytes, then the number of tags would grow proportionally to the number of cache lines. And so at some point, it would take enormous amount of time to perform all these comparisons, even though they are all done in parallel, because the cache area would be huge, and the time it takes to wire and send the signals to all these parts of the cache would be time consuming. And it's also area efficient because you need these comparators implicitly built in. So either ways, it's very inefficient to do so many comparisons to find out where my data is. And keep in mind that there is going to be exactly one place where you're going to find data, right? You're not going to store the same address in 2 different places. All right, so now how do we reduce the number of comparisons that we need to make in order to determine if it is a cache hit or a miss? So the main idea, and this sort of takes us to the idea of a direct mapped cache, is we are going to try and restrict the number of cache lines that a given cache block can be stored in. So if you think about our basic baseline design, a given cache block, let's say the first one we have with the tag 0, it can pretty much go into anywhere in these cache lines, right? So depending on which block gets evicted, I would use that cache line to store this block, right? So this freedom comes at the cost that I just explained earlier, which is that you need to do a lot of comparisons. So the solution is to restrict the number of cache lines that a given cache block can be placed in. How do I do that? Well, maybe I can think about this cache like an index structure, similar to how you think about an array and how you use an index to access an array. You can maybe think about this cache as an array with 4 elements. And you will want to use index to determine which element in the array you want to use. So how do I create this index? Well, obviously it has to come from the address, because the address is what you're trying to access. And we have already used up 1 bit for the block offset for this example. Now maybe I can use the next few bits as the array index, right? So in this case, I have 4 cache lines, 1, 2, 3, and 4, right? So maybe I need 2 bits then. So if I have 2 bits from my address, I can then use that as an index to determine which of these 4 cache lines I should use to store a given cache block. Right? So as an example, let's say for the first cache block, the array index would be 0. So I would be forced to store it in the first cache line. For the next cache block, the index is 1. So I would be stored to store in this cache block, cache line, second cache line. Similarly, the third one will be stored here, the next one will be stored here. And now if you look at my tag 4, the last 2 bits, these 2 bits that I have been using as an index, it is 0, which means that it will map to the same cache line as the block address 0. So block address 5 will map here, block address 6 and 7. So when I talk about block address, I'm talking about the tag so far, right? The tag that we had in our original design. I'm talking about that as a block address because I don't really need the block offset, which basically tells me which byte in the block. So the block address is effectively everything in your address except the block offset. So the block offset mapping would look something like what I'm showing here if I choose 2 bits to index into this array of cache lines. And so I can continue this even so 7 would basically correspond to the last address that we have here. So you will notice that there is exactly one place for every cache block to be stored, and that's good because now when I have an address, let's say I want to figure out do I have the cache block with the tag 100, which is value 6, I can go and check, well, is the tag matching the value 6, and if so, then I can check if it's a cache hit or a miss. I don't have to check all the tags. I just need to compare it to the tag that corresponds to the cache line that I can store this particular block in, right? So the upside of using index is that it reduces the number of tag comparisons to exactly 1, because the index tells me which cache line I can store that block into, and I would retrieve the tag stored in that cache line, and that's the only tag I need to check. Now, even though you may be wondering, do I really need to do a comparison? Because I know exactly which cache line I'm going to store in, so just go and access the data. Well, you don't know which of the different cache blocks that can map into that cache line is stored at any point. So for example, in this first cache line, I could either store the block address 0, right? Or I could store the block address 4. How do I know which one I have stored at any point? Well, I have to check the tag to figure that out, okay? All right, so the last point I want to make here is the tag now doesn't have to be everything but the offset. I don't have to explicitly store the index part as part of the tag, because just like what we did before where we said we don't need to store the block offset because it's always going to be the same, the address, the tag that is mapping into a given cache line, you would notice that it always has the same 2 bits for the least significant bits, right? So 4 is going to be 100, this is going to be 00, so you'll notice that the last 2 bits are always zeros. Well, that's not a coincidence, right? Because we intentionally used the last 2 bits in the tag as an index. So it's always going to be that. So the index does not have to be stored explicitly as part of the tag. So now my tag is going to be the entire address, but it doesn't have the index part minus index, because when I say minus index, I mean the part that contains the index. Maybe a better representation would be, so if I have an address, previously I had broken that into tag and block offset, but now I have used a few bits here as index, which we just argued you don't need to store as part of the tag. So that part goes away. So this is my full address, and in that address I have three components. One is a block offset, which is defined by the size of the cache block, and then I have the cache index, which is defined by the number of cache lines you have. So the number of bits I need, the index size, is going to be log to the base 2 of the number of cache blocks, right? So in this example that we had 4 cache blocks, so that's log to the base 2 of 4, and the answer is 2 bits. And that's why we used 2 bits for the index. And before we had talked about how it's going to be 1 bit for the block offset because there are 2 bytes per block. And then the remaining is going to be tag, and given that this is a 4-bit address space, which is what we have been talking about, so the tag would be just 1 bit. Let me more precisely define the terms we talked about, and I will also go through a simulation of a cache architecture to illustrate the idea of a direct mapped cache. So the cache that we have been talking about all along, there is a technical name for it. It's called fully associative cache. And the reason why it's fully associative is because a given cache block can be stored in any one of the cache lines in the cache. So in this example, a cache block can reside in any 4 of the cache lines shown in the picture. And like we talked about, this has a tremendous cost in terms of tag comparisons, both in terms of the area cost of implementing a CAM for these tag comparisons, and also the time it's going to take for you to perform that CAM lookup for every address. And both of them scale as you increase the number of cache lines. Now, the alternative that we talked about is called the direct mapped cache. And the idea here is that instead of giving the freedom to store a cache block in any cache line, we are going to say there is only one cache line where a cache block can be stored in. And that cache line is going to be determined based on the index, which is derived from the address. So we are treating the cache, which consists of a set of cache lines, is effectively an array, and then we are going to index into that array to select the cache line. And the index that we are going to use comes from the address. So we had used previously 1 bit for the block offset, so now we have 2 bits for choosing one of the 4 cache lines. And whatever that is left over from the address is going to be your tag. Now, we also talked about the fact that many cache blocks can map to the same cache line, and that is highlighted by the colors that are shown. So any cache block with the address index 0 will map to the first cache line. So these 2 cache blocks will map to the first cache line. This one and the blue ones will map to the same cache line. So when I say they map to that cache line, what I mean is when the program accesses one of these cache blocks, they will be stored in the corresponding cache line, and they're all color coded to help us understand where they can get stored. And the one point that you want to take away from this is at any given time, only one of the cache blocks that can map to a cache line can be stored, obviously, right? Because the cache line has space only for one block. So I could either store this blue block or this blue block. I cannot simultaneously store both of them at the same time in my cache. because of the restriction that I have imposed on myself, where I say these two blue cache blocks must be stored in this blue cache line, and so at any point only one of them can be stored. So that is the trade-off that we are making here, because it's quite possible that I'm not really utilizing the other cache lines at all, right? And the only two blocks that a program is interested in are these two blue blocks. So in that case, I would be not utilizing all the available space in the cache. And these two blue blocks are going to compete for this one cache line. So they may kick each other out as a program accesses them. And we're going to refer to the misses, cache misses incurred because of such conflicts between each other as a special type of cache miss called conflict cache misses. So we're going to come back to this idea of a conflict cache miss later on and define them more precisely, but I want you to get a sense of what that is. So here is another representation of what a direct map cache looks like. So an address again is composed of the block offset, the line index, which is what we talked about to select the cache line in a cache, and the remaining is a tag. So you would use this as a index into the tag array. So think of this exactly like how you would think about accessing an array in your C program, where you will say something like a of I, right? So where you access the ith element in the array A. Similarly here, the line index tells you access the ith cache line. When I say access, what I mean is the cache block corresponding to this address would be stored in the cache line corresponding to this line index. And there's a data array corresponding to that. And so whenever I want to access the cache, I'm going to take this line index, get the access to the tag, and then compare if this tag matches with this tag or not. And so if the tags match, then I know that it's a cache hit, and then I can go and retrieve the data that is stored in my data array, and then provide the block offset to select one of the bytes in the cache block, because that's what I'm ultimately interested in for a given address. So one of the properties of the direct map cache is that for a given index there is exactly one cache line where it can be stored. So we also talked about conflict misses. So here is a pathological example where we are assuming that addresses A and B have the same index bits, so they map to the same cache line. As a result, only one of them can be stored in the cache. It doesn't matter how big your cache is, because they both map to the same cache line, only one of them can be stored at any time. And so if you have a program that is going to access A and then B, A and then B, you can see that when I access B, A has to be kicked out. So when I access A again, that would be a miss. So first time I access A, that's a miss. First time I access B, that's a miss. But the second time I access A, it's also a miss because B kicked me out, right? And then second time I access B, that would also be a miss because A would have evicted B. So each one of these accesses ends up being misses. So irrespective of your cache size, for this pathological reference pattern, you would have zero hit rate. This is a pathological pattern. In reality, direct map caches perform reasonably well, but there is this trade-off that we are making where we are saying we are going to forego the freedom of storing a cache block anywhere in the cache, but in return we have to incur higher cache miss rate. So let me walk through an example, animate and simulate the cache to get a sense of how this direct mapped cache would work. So in this example, I have only two cache lines. So as a result, the index bit is just 1 bit. I still have my 4-bit address space, with 16 bytes of 16 bytes of data in memory. And so my address has 4 bits. We have used 1 bit for the block offset, so you see that there are 2 bytes in the block, and the remaining is going to be a tag, and so in this case there are going to be 2 byte tags. So anytime you're asked to simulate a cache like this, you would be given a reference sequence, and so for every address you have to split that address into these 3 components for you to be able to understand where that cache block would be stored. So the next question is, do I need to really worry about the replacement policy for direct mapped caches? Well, it turns out the answer is no, because recollect that there is exactly one cache line where a cache block can be stored, and so when you bring in a new cache block, you know exactly which one to evict, whatever cache block that is going to be stored in the cache line that you are indexing into. So we don't really need a replacement policy in this case. So let's take an address 1 and then split that into different fields. So I have done this on the right hand side, so we don't have to keep doing this again and again. So the index is 0, the tag is also 0. So I would update my cache line to reflect that. I have brought in the data, I update my register because it's a load instruction, and it's going to be a miss. I load my second address 5. Again, it is the tag is 1, index is again 0, which means that it would conflict with the tag that is currently stored in the cache. So 1 does not match with 0, which means it's a cache miss. So the current cache block would be evicted and replaced with the new cache block with the tag ID 1. So this is also a miss. So you notice that the tag changed. So now let's go to the next instruction, store, which is accessing address 2. So we have the split here. So you will see that the index is 1. Fortunately, we don't have any valid cache block stored. How do I know that? I can check my valid bit. So this is the first time I'm going to be using this cache line, and I'm assuming that it's going to be a write allocate policy. So I would bring in the data, I would allocate a cache line and bring in the data and set the dirty bit, because I just modified the data based on the R2 value. And then I have another store instruction to address 7. The index is 1, tag is 1, so index 1, tag 1. So the tag does not match with what I have stored, so it's going to be a miss. I'm going to replace it. But before I do that, I have to evict the current cache block, and I don't have to worry about doing anything else. But in this case, I have a dirty bit set, which means that I need to write back the data into memory, and then I bring in my cache block corresponding to the address 7, and I would write with the data that is stored in R1, which is 29, which I have stored here. So finally I have address 4, which I'm trying to load, and the tag for that is 1, index is 0. So I would compare this tag with this tag, and it turns out to be a match, which means it's a cache hit. And it's a cache hit because it's due to spatial locality. So remember that this is the first time I'm accessing 4, but in the past I had accessed the block containing 4 and 5, and therefore both were brought into my cache. So now I'm able to turn 4 into a cache hit because of that. So in the end we have 4 misses and 1 hit due to spatial locality towards the end.